In this chapter, chapter 19, we're going to be looking at carboxylic acids and nitriles. And then just as a heads up, in chapter 20, we're going to be looking at the other carboxylic acid derivatives. So we'll focus on the carboxylic acids and nitriles in this chapter, and we'll go on to the other ones, esters, acid chlorides, amides, and then even the acid anhydrides. So we'll talk about those. But first, let's do this one, carboxylic acids and nitriles. First of all, let's talk a little bit about the structure and the bonding. So carboxylic acids contain what we call a carboxy group. Carboxy group is the COOH. We've seen this before. So a carboxylic acid contains that, and this portion of it is the carboxy group. You'll often see the carboxylic acids abbreviated as either COOH or CO2H. What's important to remember, though, is that the carbon is bonded to both of those oxygens. The oxygens are not bonded to each other. When we look at the bonds in carboxylic acids, we'll find that we truly do have a double bond and a single bond. The double bond in the carbon-oxygen double bond is shorter and stronger than the single bond between carbon and the other oxygen. If we look at if we look at the carbon, it is sp2 hybridized, so it's very close to the ideal angle of 120 degrees, 119, 120, in that range. We can have varying bond angles in there. And if we look at the bond between the oxygen, the single bond between the carboxylic acid and the carbon-oxygen single bond in that versus the carbon-oxygen single bond in alcohol, we'll find that that can be explained because in the carboxylic acid, the carbon is sp2 hybridized, whereas in the alcohol, it is sp3 hybridized. And because those sp3 hybrid orbitals, they have more p character, less s character, they're going to be longer than the sp2 hybridized orbitals. So that would explain that. We'll also find that the carbon-oxygen bonds and the oxygen-hydrogen bonds are quite polar. And when we look at physical properties here in just a little bit, we'll see how that affects their properties. And then here is an electrostatic potential chart for acetic acid. It has two very electron-rich oxygen atoms. So the oxygens have significant electron density, partial negative charge on each of those. And then, of course, the hydrogen and the carbon both have a partial positive charge. The hydrogen has a very significant partial positive charge, and it is quite acidic. We will talk about the acidity of it later in the chapter as well. Nitriles, since we're throwing nitriles into this, nitriles, there's not really an ideal place to put nitriles because they are definitely related to carboxylic acids, and there's reactions that we can do with them that are similar to some of the derivatives, but they're also very different. So in a nitrile, we have a cyano group where it's a carbon-nitrogen triple bond bonded to some alkyl group. If it happens to be bonded to hydrogen, it is not a nitrile, it's hydrocyanic acid, HCN, which is very, very poisonous, just in case you need a reminder. So we're going to find that there are some key differences, but there also are some key similarities. Nitriles do not have a carbonyl group, so there's not a carbonyl, there's not a carbon-oxygen double bond, so they're very different than other carboxylic acid derivatives, but they do have a lot of the similarities. So what makes them different here is that they're sp hybridized. We have the 180-degree angle, whereas in the carboxylic acid derivatives, sp2 hybridized with the approximately 120-degree angle. What makes them have similar reactivity as some of the acid derivatives is that the carbon has a partial positive charge and the nitrogen has a partial negative charge. So we've got that polar bond, and it's capable of being an electrophile. So nucleophiles are capable of coming in and reacting with that carbon. And so a lot of the reactions that we can do with our carbonyl groups, we can also do with nitriles. So, and then as I mentioned, sp hybridized, that's what gives us that 180-degree angle. All right, so we're going to look at nomenclature for both the carboxylic acids and nitriles. We'll start with the carboxylic acids, and when we're doing IUPAC nomenclature, we will identify that it's a carboxylic acid by changing the last letter E in the name to an oic acid. So propane becomes propanoic acid. Butane becomes butanoic acid, and so on and so forth. If we have the carboxy group attached to a ring, we can name the ring and simply add the word carboxylic acid. So like if we have a carboxy group that's attached to a cyclohexane, we would call it cyclohexane carboxylic acid. When it comes to numbering, if we have a straight chain, the carboxy group, that carbon is going to be carbon number 1. And if we have a carboxy group attached to a ring and we call it, like cyclohexane carboxylic acid, then wherever that carboxy group is attached, that's going to be carbon number 1. And then we're going to apply all of our other usual rules of nomenclature as we've gone through and added these additional rules. And so we'll go through and practice some of those here shortly. Now, there are quite a few common names that have been around for a long time, and so we have to kind of keep those in mind whenever we are looking at, particularly if we're looking at older literature where the names are there. But in addition to that, some of these names are so entrenched that we don't use the IUPAC nomenclature for them very often. For example, under the IUPAC nomenclature, where we have a 1-carbon chain, I guess it's not really a chain if there's only 1 carbon, but if we have a 1 carbon and it's a carboxylic acid, we would call that methanoic acid. But most people don't call this methanoic acid. Most of us call it by the common name, which is formic acid. So formic acid is our simplest carboxylic acid. And then here, if we've got 2 carbons, again, under the IUPAC nomenclature, we would refer to this as ethanoic acid. But for the common name, we're going to refer to it as acetic acid. And most people will call this acetic acid. All right. Under the common name, the IUPAC name, this would be propanoic acid. And under the common name, it's propionic acid. And so those are so close that sometimes they get confused. But propanoic versus propionic. Butanoic acid, under the common name, is called butyric acid. We'll talk about this one here in a little bit when we talk about the interesting carboxylic acids. Pentanoic acid, we call valeric acid. Hexanoic acid, its common name is caproic acid. And if you're wondering, all of these kind of smell. They all smell kind of bad. If we were to go with just the straight up IUPAC nomenclature for this, we would call this benzene carboxylic acid. But almost everybody is going to call it benzoic acid. And in fact, there are IUPAC nomenclature rules about using benzoic acid. So we will work with benzoic acid. Now, when it comes to the common naming procedure, we saw this similar thing when we were talking about aldehydes in the previous chapter, but when we're using the common names, we use Greek letters to indicate the location where substituents might be. And this gets a little bit confusing. Because for our IUPAC nomenclature, carbon number 1 is the carbonyl carbon of that carboxylic acid. And so that's carbon 1, and the second carbon is carbon 2, and so on and so forth. But when we're using the common nomenclature, what we call carbon 2 for IUPAC is the alpha carbon. And so alpha carbon just means the adjacent carbon. And so that's the alpha carbon. And then we could do beta, gamma, delta, epsilon, whatever, as we go on to look at other carbons. The last carbon in the chain is sometimes called an omega carbon, meaning omega being the end of the Greek alphabet, just meaning that that's the last carbon. And in fact, there are fatty acids, which are carboxylic acids, that have double bonds. And if the double bond is the third bond from the end, it's referred to as an omega-3 fatty acid. So you will see that is fairly common. So and so that is one of the ways that we designate those kinds of double bonds. All right, so there we go. Carbon 2 is the alpha carbon, and carbon 3 is beta, and so on and so forth. So that sometimes can get confusing, so make sure that you get that down. Now, when it comes to naming dicarboxylic acids, where we have two carboxy groups, we can call them diacids. That's the nomenclature that we use for it. And so here are a couple of dicarboxylic acids, or diacids. We can use the suffix dioic acid. And so that suffix just means that there's a carboxy group at the end of each chain. So for example, in the IUPAC nomenclature, where we have two carbons, we would call that ethane dioic acid. So it's the ethane dicarboxylic acid, so ethane dioic acid. Of course, hardly anybody will use ethane dioic acid when they're describing this molecule, because it is most commonly known as oxalic acid. Propane dioic acid, that's where it's on 3 carbons. Propane is 3. And then dioic, there's two carboxy groups. Well, we refer to that as malonic acid. And again, as we head into chapter 21, we're going to talk about malonic acid, the malonic acid, and the malonic acid synthesis, and the malonic ester synthesis, and so on. So we will refer to malonic acid quite a bit. If we have 4 carbons, butane dioic acid is the IUPAC name, but again, most commonly referred to as succinic acid. If we've got the metal salt of a carboxylic acid, we'll see this quite a bit because acids are acidic. We can deprotonate them and get the conjugate base. Well, those we're going to name by just taking whatever the name is that ends in "ic," and we're going to change the ending from "ic" to "ate." So, for example, if we've got acetic acid, we deprotonate it with sodium hydroxide, we will get sodium acetate. If we have propanoic acid and we deprotonate that with potassium hydroxide, we will get potassium propanoate. So again, propanoic acid becomes propanoate, acetic acid becomes acetate. And you'll notice here we've got one that is a common name and one that is an IUPAC name, and they both work the same way for salts. Now, for naming of nitriles, it's a little bit different. And I'm going to point out something once we go through this that is different than sometimes we would think about this. So nitriles are named as alkane derivatives. So we don't combine it, as we don't like drop the suffix, we just add it to the end. So what we'll do is we'll find the longest chain that contains the cyano group, the CN group, and we're simply going to add the word nitrile to the end of that parent alkane. And here is an example. We've got 1, 2, 3, 4 carbons. We want to number so that carbon 1 is the cyanocarbon. So 1, 2, 3, 4. And so since this is 4 carbons, we're going to call this butane nitrile. Now, what's a little bit odd about this is that typically when we take butane and then add a word to it, it means that we have something else attached to the butane. And this is a little bit different in that we've got the cyanocarbon is part of the 4 carbons that makes up butane. And so instead of saying we have a butane and we add a nitrile to it, it's a butane that contains the nitrile. And I know that doesn't sound like a big difference here, but there are 4 carbons. That's why we call it butane. But one of those carbons is a cyano group. All right, here we have another one. We're going to count from this side. So 1, 2, 3, 4, 5, 6, 7. So 7 would be heptane nitrile. So heptane nitrile. And of course, we've got methyls at the 4 and 5 positions. So we're going to refer to this as 4,5-dimethyl heptane nitrile. All right, just a little bit more on nitrile nomenclature, and then we're going to do some practice problems. So when it comes to the common names of nitriles, there are quite a few common names. They are typically just derived from the carboxylic acid having the same name, the common name for the carboxylic acid, but replace the ic with O-nitrile. So for example, acetic acid is where we have 2 carbons as a carboxylic acid, and if we just change the ending from ic to O-nitrile, then that is acetonitrile. And we can do the same thing with other ones. All right. When the cyano is a substituent, for example, here on a ring, we have it as a substituent, then we can simply call it a cyano group. And then here is, this one's 2-methyl butane nitrile, so there's 4 carbons in that butane group, and then a methyl as a substituent. Over here, this is an example where we have cyano as a substituent. And so if we call this whole thing cyclohexane carboxylic acid, then that carbon is implied to be carbon 1. And then here, where at our 2 position, we have a cyano group. So the main functional group here is the cyclohexane carboxylic acid, and we have a cyano group that is attached. So let's look at number 34 on the in-class assignment. We'll switch over here. All right, lighting looks good. All right, I'm going to pause it for a second. All right, so that looks pretty good. All right, so we want to give the IUPAC nomenclature here for each of these. So here we've got a carboxylic acid, and it's in a chain, and we want the longest chain, and we'll call this 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So 8, that means it is octanoic acid. So octane, we change the E to oic acid. So that's octanoic acid. And we have methyls at the, we have 2 methyls at the 4 position and 2 methyls at the 5 position. So we're simply going to refer to this as 4, 4, 5, 5, tetramethyl octanoic, and then space acid. So 4,4,5,5 tetramethyl octanoic acid. All right, it looks like I added an extra C in there. I'm going to fix that real quick. So octanoic. I didn't want to misspell that. So OCTANOIC, octanoic. All right, so now for this one, this one is a carboxylate salt. So we're gonna name it as the acid, but then change the ending from ic to 8. And we'll number the longest chain, starting with the carbonyl. So 1, 2, 3, 4, 5. So 1, 2, 3, 4, 5. All right, yeah. So even though there are 6 here, we want to include that carbonyl as part of our longest chain. So 5 would be pentanoic acid. I'm going to write that down. So pentanoic acid. But we're going to change the ending from ic acid to 8. So this is going to get, I'm just going to put a single line through there, and this will be pentanoate. All right, so we're going to put 8 right after the O. And then we have an ethyl group at the 2 position, so it would be ethyl pentanoate. And then we want to indicate what this metal is, and we can indicate what that metal is by putting it out front. So we'll do lithium space 2 ethyl pentanoate. All right, and that is the name of that one. All right, well, here we've got a cyclopentane ring that has a carboxylate on it. And since it has that carboxy group, or not the carboxylate, but the carboxy group, the COOH, we're going to name this and put this as carbon 1. And then there's a substituent there, and then there's a substituent over here that's at position 2. So we're going to go counterclockwise. All right, so this part is called cyclopentane carboxylic acid. So cyclopentane carboxylic acid. And then, and I'll go ahead and write that down. So cyclopentane carboxylic acid. All right, so we have cyclopentane carboxylic acid. Now we're going to put the substituents on there. The substituents are an ethyl at the 1 position, so 1 ethyl. And at the 3 position, we have, this is an isobutyl, so 3 isobutyl. And then it's just a matter of putting these in the correct alphabetical order. Remember, when we have iso, we include I as part of the alphabetizing. So we're going to do 1 ethyl, 3 isobutyl, cyclopentane carboxylic acid, and it just all rolls together. So 1 ethyl, 3 isobutyl, cyclopentane carboxylic acid. All right, so that's a nice long name. Just, you know, yeah, that's a really, really long name. But that is a unambiguous name for this. All right, well, we're going to name this whole portion of it as a benzoic acid. And it is acceptable to use benzoic acid as part of your IUPAC nomenclature. It has been incorporated. So we're going to call that benzoic acid, and then we need to number it for substituent purposes. So that's position 1, and to give our next group, which in this case is nitro, the lowest possibility, we'll call that 2. We'll go clockwise, 3, 4, 5, and then 6. There's nothing there on 6. All right, so we've got benzoic acid, and then we just need to figure out what the substituents are here. We've got a 2 nitro, so a nitro at the 2 position. We've got a 4 ethyl and a 5 bromo. All right, now we just have to put those in alphabetical order: bromo, then ethyl, then nitro. So we'll do 5 bromo, 4 ethyl, and 2 nitro. And then benzoic, so all that's one word, no spaces there. And then finally, we're going to put a space and then put the word acid after that. So 5 bromo, 4 ethyl, 2 nitro, benzoic acid. All right, here again, we've got another carboxylic acid salt. So we'll number it the same way: 1, 2, 3, 4, 5, 6. So number the same way we do for a carboxylic acid, where our carbonyl carbon is carbon number 1. So there we go. We've got, that's carbon number 1. And so since it's 6, 6 is going to be hexanoate. Hexanoic acid will turn into hexanoate. So we'll put hexanoate. So that is the name of this. We do have a sodium attached to it. That's going to go out front. That's not, we're going to put all the things that are directly attached to the chain immediately before. We're going to put the sodium out front. And then we've got a methyl at the 2 position. So we have a 2-methyl. And that will take care of everything. So again, sodium is out front. Then space, 2-methyl hexanoate. And there we go. All right, this one, oh my goodness, there's a lot of stuff, but just be very systematic and let's find the longest chain. So carbon 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so that is decanoic acid. All right, so that's the chain is decanoic acid, and we have several different substituents. At the 3 position, we have a methyl, and at the 5 position, we have an isopropyl, and then finally at the 7 position, we have an ethyl. So we'll do that 7-ethyl. So with that, we want to put those in alphabetical order. Again, we're going to include the I for alphabetizing purposes. We've got E, I, and then M. So ethyl is going to come before isopropyl, which will come before methyl. So we'll put 7-ethyl. All right. 5-isopropyl. 3-methyl, and I need more space. There is no space in between here, so we're just going to put decanoic, and then finally a space, acid. So 7-ethyl, 5-isopropyl, 3-methyl decanoic acid. And again, there's no space in between the methyl and the decanoic acid. All right, for this next one, we're going to name this whole component as benzonitrile. All right, so that's benzonitrile. Attached to the benzonitrile, we've got a chloro and a bromo. We're going to number from there 1, and then to give our next substituent the lowest possible number, we'll go clockwise, so 5 and then 6. Our bromo is at the 3 position, and our chloro is at the 4 position. All right. Bromo, of course, comes before chloro alphabetically, so we'll put that together as 3-bromo, 4-chloro, benzonitrile. What a lovely name. All right. On this one, we need to keep in consideration that we want our cyano group to be part of whatever our longest chain is. That means that we may give up whatever the actual longest chain is in order to include that cyano group. And that's definitely the case. So 1, 2, 3, 4, 5, 6, 7, 8. And let me make sure I included all those. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so we've got all of those. And then here at the 2 position, so that is octane nitrile. All right, so that's octane nitrile. And at the 2 position, we have an ethyl. And at the 3 position, we have a propyl. So now we can put all that together. Ethyl comes before propyl alphabetically. So we'll have 2 ethyl, 3 propyl, octane, nitrile. All right, so let's real quickly look at some of the physical properties of carboxylic acids and show what distinguishes them from other things. So carboxylic acids, they have these dipole-dipole interactions because of the polar carbon-oxygen bonds and oxygen-hydrogen bonds. And so that does give us this, we do get strong dipole-dipole interactions. And in fact, we get intermolecular hydrogen bonding because of the OHs. But the thing that makes them kind of unusual is that we often will get a situation where we have a hydrogen bond between an OH and the carbonyl on between 2 carboxy groups. And on the same 2 carboxy groups, we get another OH. And because of this, we get double hydrogen bonding. And so when this happens, these are pretty firmly attached to each other. It's not nearly as strong as a covalent bond, but they are attached to each other. And so they spend most of their time in these groups of 2 that we call dimers. So we have 2 of these intermolecular hydrogen bonds that hold them together in dimers. And because of this, we end up getting higher melting points and boiling points than you would typically see for molecules that size, even with hydrogen bonding. So if we compare to alcohols, alcohols of similar size, so here is propanol, and we compare that to acetic acid, we're going to get about double the hydrogen bonding, and you'll see what that does to the boiling point. It goes from about 97 up to 118. So we get a significant increase in the boiling point. We also get some similar kinds of increases in melting points. When it comes to solubility, we're going to find that carboxylic acids generally are just soluble in organic solvents like benzene and dichloromethane and our typical organic solvents. And we'll find that the carboxylic acids, because of the strong hydrogen bonding interaction, they tend to be soluble when we have 5 or fewer of the carbons, and they tend to become insoluble when you get up over 5. If you're at exactly 5 carbons, you will find that it will be somewhat soluble, but it will reach a point where you can't get any more to dissolve. So with pentanoic acid, we kind of reach the limit on that. All right, so when it comes to spectroscopy for these compounds, we can look at the spectroscopic properties of the carboxylic acids. So we'll get the spectroscopic properties of these carboxylic acids. In carboxylic acids, the most distinct characteristics are in the IR and the proton NMR. And we'll have one distinctive feature in the carbon NMR. In the infrared, we have our typical carbonyl stretch, which comes in close to 1700, a little bit over 1700 for your average carboxylic acid carbonyl. The OH stretch is I won't say a little bit, it's significantly different than the OH stretch for an alcohol. For the carboxylic acid, that stretch goes from about 2500 to 3500, which is a very broad peak. Whereas in an alcohol, it's from about 3600 to 3200. And you'll also see that there is a difference in the shape. I will show you an example of both the alcohol and a carboxylic acid on the next page. For the proton NMR, the most distinctive features are going to be the acidic hydrogen, the one that is on the carboxy group. It shows up all the way out at 10 to 12 parts per million. So it's very far downfield. And the reason for this is because it is significantly deshielded. The electron density is pulled away from those hydrogens, and so they show up all the way down downfield at 10 to 12 parts per million. There's really not much else that shows up down there. You recall the aldehydes were from 9 to 10, and then this carboxylic acid shows up from 10 to 12. And then the alpha protons, so those that are directly adjacent to the carbonyl, they show up from 2 to 2.5. And that's very typical for alpha hydrogens on carbonyl compounds. In the carbon NMR, there's really one distinctive thing, and that is where the carbonyl shows up. So that carbonyl carbon typically shows up very far downfield, very deshielded in the 170 to 210 parts per million. Typically a little less deshielded than aldehydes and ketones, but still pretty far downfield. All right, here I want to compare the IR spectrum of butanoic acid with butanol. So here, this is that big peak that I was telling you about from about 3,500 to 2,500. It's this whole thing. And in fact, it completely overwhelms the carbon-hydrogen stretching that we see because there's sp3 hybridized carbons that show up here. The OH peak is much broader and goes over all of that. So it kind of goes, a big sort of double curve there. For alcohols, we'll recall that alcohols have still a very broad OH peak, but it is much narrower compared to the carboxylic acid, and will typically show up from 3,500 to 3,200. I expect you, if I were to show you two similar compounds, but the difference is that one is an alcohol and one is a carboxylic acid, you would be able to distinguish between those almost instantly just by looking at the two spectra. So carboxylic acid, very broad absorption, and for the alcohol, much narrower, but still quite broad compared to other peaks. So let's look at number 8 on our in-class assignment. All right, so we just want to say, how could we use infrared spectroscopy to distinguish between these three, or among these three different things? So we're going to leave out our sp3 carbon hydrogen, because all of them, I'll just put all, have carbon sp3 hydrogen. So that's really not going to be a way that we can distinguish, because all three of those are going to have them. So we'll want to look and see what makes this distinctive. Well, here we've got the carbonyl. So we do have our carbon-oxygen stretch that is going to be at about 1,700, 1,710 reciprocal centimeters. So that's going to be our typical range for most carbonyl compounds. And since this has a carbonyl, it's right about there. For the OH, because it is a carboxylic acid OH, we're going to find that it's from about 3,500 all the way down to 2,500. Reciprocal centimeters. And that is going to be sort of the dominant peak there. On this one, it's definitely going to have our carbonyl that's at about 1,700, and is probably going to be very close to that of the carboxylic acid, so about 1,710. All right, it could move around a little bit, and then the key thing that differentiates it from this is that we have no OH stretching. So with no OH stretching, it will be sort of by itself. And then finally, on this one has no carbonyl, so we won't see anything in the 1,700 range, but we will see an OH stretch, and our OH stretch is going to be from 3,600 to 3,200. And that's because this is a very typical alcohol. So 3,600 to 3,200. All right, and again, like I said, they're all going to have carbon sp3 hydrogens, so they're all going to have those peaks that are from about 3,000. So these are all from 3,000 to 28 250 reciprocal centimeters. But these are going to be the so CO and the OH, and a very broad OH, no carbonyl, or it does have a carbonyl but no OH, and this one has no carbonyl but it does have an OH. So these should be pretty easy to distinguish among in a infrared spectrum. All right, so I want to look at just a few more things here before we wrap up this particular video. We'll be looking at the proton and carbon NMR for propanoic acid. So for the proton NMR, the most distinctive thing is that acidic hydrogen, the one that's on the carboxy group, is all the way down. And look, it's kind of broad, and it's down there all the way downfield near 12. And again, you just don't see much else that's out there 10 to 12. So that's definitely tells us it's a carboxylic acid. The two hydrogens here are to be expected. We've got one that is adjacent to the carbonyl. It shows up here at about 2.5. And we've got one that's separated. It's closer down to 1. And because we've got two hydrogens here and three hydrogens here, we should expect a quartet for this one and a triplet for this one. And so these are coupled to each other. We don't get any coupling to the hydrogen here. This will be a singlet, and it's typically a little bit broad because of hydrogen bonding. When we come over to the carbon spectrum, we'll find that again our most distinctive peak is going to be the carbonyl carbon. And you'll see here it's at about 180. If you recall, aldehydes are typically out at about 200, and our ketones were usually 190 to 200. And so this is usually not quite as far downfield as the aldehydes and ketones, but it is still pretty far downfield. The carbon adjacent, so the alpha carbon that is there adjacent to the carbonyl, you'll see it's a little bit downfield from the other one because it is a little bit deshielded compared to that carbon that is the CH3 on the end. Okay, so we'll talk here about the spectroscopic properties of nitriles. So when it comes to nitriles, as far as what we can expect from them, the IR is going to be very distinctive, and that that there will be, because of that triple bond, there will be a stretching frequency near 2250 reciprocal centimeters. So that'll be the wave number for that. This is also where you would find a carbon-carbon triple bond, and it's about the same intensity, and it's also fairly sharp like this peak. So it can sometimes be a little bit challenging to distinguish between a carbon-carbon triple bond and a carbon-nitrogen triple bond, but that is definitely a factor. And then the rest of this is all pretty simple because we've got a whole bunch of carbon-hydrogen sp3 carbons bonded to hydrogen, so 3000 to 2850, nothing unusual there. In the NMR, our alpha protons are going to be from 2 to 2.5, just like what we would expect for an alpha proton on a carbonyl compound. Similar kind of electronic environment, so 2 to 2.5 is very typical there. And then for the carbon NMR, the carbon in that nitrile is going to show up at about 115 to 120. So it's not nearly as deshielded as the carbonyl. So 115 to 120 is a very typical range there. All right, so we're going to look briefly at some interesting carboxylic acids and things that make them different than some of our other compounds. We'll start with the simplest carboxylic acid, and that is formic acid. So formic acid is the simplest carboxylic acid. All right. It has a very acrid odor. In fact, you'll find most carboxylic acids have a very unpleasant odor. And I think most people would think that even this other one, which I'm going to point out, has an unpleasant odor, although we're kind of used to it because it is the acid that's in vinegar. But let's go back to formic acid for a second. If you were to get some formic acid in a bottle and smell it, you would see that it is quite a quite biting smell to it. Formic acid is the acid that if you get a regular ant bite, like a red ant, then that ant bite contains formic acid, and that is part of what gives it the sting. Now, that is not what gives like a fire ant bite its sting. That includes some alkaloids, and those alkaloids, they're a whole different ball game, which is why they can hurt in all kinds of different ways. A little bit of formic acid, it will sting, but it probably is not going to be debilitating as some other ant bites are going to be. Interesting, the Latin word for ant is formica, which is how we get the name formic acid. So that is kind of cool. All right, for acetic acid, that, as I mentioned, it is the sour component of vinegar. And so whenever you have alcohol that ferments, if the alcohol, the ethanol, gets overly oxidized, it will form acetic acid. And so we'll get add another oxygen to the carbon, and we get acetic acid. And that makes the wine taste bad. In fact, the word vinegar means wine bad, right? It means it's wine that has turned bad. Of course, we find a way to take that wine that has turned bad and turn it into salad dressing. So, and just a little bit of acetic acid goes a long way in your vinegar. Typical vinegar is about 5% acetic acid, and it has a very strong odor to it. If you get concentrated acetic acid and smell it, it is much, much more powerful smell. All right, some other common carboxylic acids, butanoic acid, which its common name is butyric acid. That name butyric acid comes from the Latin word for butter. When butter goes bad, one of the compounds that gives it particularly bad flavor and smell is going to be butyric acid. And as I mentioned, most of these carboxylic acids have very strong odors to them. And so butyric comes from the word butter, which I think that's kind of cool. Caproic acid is the common name for hexanoic acid. And if you have ever been in a locker room that smells like junior high, then you know what I'm talking about. It's got the dirty socks and locker rooms and dirty laundry. It's sort of a very foul smell. If you don't wash your gym clothes right away, they have that really funky odor to them. Well, that comes from the caproic acid. And so caproic acid, the word caproic actually comes from the same, like Capricorn or caper, which is the word for goat. And so it comes from the word for, oh, this smells like a goat. So that is hexanoic acid, and again, foul smell. By the way, one of the things you can add to your laundry, if you have gym clothes, you can use a moderately strong base. Instead of using bicarbonate, you can use sodium carbonate, and that helps to remove some of the caproic acid that forms when you have your gym clothes. Now, if you let them mildew, there's not much you can do about that other than like bleach and all kinds of nasty stuff. So, all right, oxalic acid and lactic acid. Oxalic acid, I think we saw this one a little bit earlier. Oxalic acid is a diacid. Yeah, when we were talking about diacids. Oxalic acid is a diacid, ethane dioic acid. And it actually shows up naturally in a lot of different vegetables, particularly spinach and rhubarb are pretty rich in oxalic acid. And that's oxalic acid is a component of your diet, so you do need to have a little bit of it in your diet. If you get too much oxalic acid, it can lead to oxalate, particularly with other metals like calcium and things like that. It can form deposits, and those deposits can cause kidney stones. Now, you have to eat a lot of spinach for this to be a problem, but it's something to keep in mind if you are having problems with kidney stones, and you will know if you do because it's very unpleasant. Then you might want to cut back on things that are rich in oxalic acid. And if you're uncertain, talk to your doctor, and they will help you with that. Lactic acid. So lactic acid shows up from the oxidation of certain sugars like galactose. When the lactic acid oxidizes, you can get, or when the galactose oxidizes, you can get the lactic acid. And so that is, again, a very funky taste. All right, well, we're at 50 minutes, so I'm going to stop this recording, and on the next recording, we're going to talk about aspirin and related compounds.